Hi everyone, welcome back to BCodeTube. I want to revisit this project because what I really want to check now is these two libraries that are from CPP, and they have the similar APIs as NumPy. So the way to use them could be almost one by one replacement from NumPy. So if you have your code in Python with NumPy, if you use these libraries, you can quickly convert them to C++. So this is the first one, NumCPP. It says here a templatized header only C++ implementation of the Python NumPy library. So from here, basically you can download the zip and just grab the include folder. It has this main header and all the other headers are here. So you just need the include folder in your project. For the second one, xtensor. So this is the project. It is also a header only library. So you can just grab this library, but it has some dependencies, especially on Windows. On Linux, let me grab here. On Linux, I'm on Ubuntu, so on Ubuntu I can just install from here xtensor dev, and I also installed this libxtensor dev. On Ubuntu, the XTL is the dependency for xtensor, so it was installed automatically. If you are on Windows, you will have to install XTL manually. It doesn't come with xtensor, and also this DBB for parallelism. I only installed this libdev on Ubuntu. On Windows, I found this one TBB that is a replacement that can be used as the same as TBB on Ubuntu. And also this openblas, I also had to use this on Windows. On Linux, I just used this extensor blast. And also, if you want SIMD implementation, SIMD instructions on Ubuntu, I can install just this one, libxmddev. But on Windows, you have to install it here. Basically, CMake install and put the prefix on your path. The same here, just CMake install and then put on your path, and the same for the XTL, CMake install and then put the installation on your path. This the same, there is a CMake here. You can just do a CMake install, put on your path. And for BLAS, you download the binaries and put in your path. Okay, I'm not gonna show step by step on this video, but if you have any questions, just ask and I'll try to help. So this is the code for the project. The Python one, we did this in the previous videos. I think the first or second video, I did it step by step, line by line, right? I'm not gonna show line by line here because I already did that. The idea here is just pinpoint the difference from using NumPy and using NumCPP, or here in this case the xtensor library. Okay, I'm just gonna pinpoint the differences. So seeding the library here in NumPy, we use like this. For NumCPP is almost the same, and for the xtensor is also almost the same. We have the namespace already added by the library in both cases, so the library adds the namespace for us, and we can just use it. Then for the next thing is when we converted, we created the dataset manually, extracting the image files, and then we had to convert to NumPy. So basically we get the pixel values here, and the label. So the label is the first column, the pixel values are the rest of the columns, and then we convert to a NumPy here as NumPy as array. For NumCPP, we create the matrix like this, the float matrix. We set the first column we loop through each image, and then we set the first column as the label and all the other columns as the pixels. Almost the same in xtensor. We create the matrix, then on the shape that we pass here, here we pass the shape as multiple parameters. Then the first column is the label, and the rest of the columns are the pixels. Okay. Then to get the first column, so get y. Let me show the NumCPP first. So get y, we do a R slice to retrieve all the rows, same here, and we get just the column 0. In xtensor, we return a view of that matrix on all the rows and only the column 0. This comment is actually for here, because to get the x, we have all the rows again, but then arrange from 1 to the rest of the columns. So to enable this syntax with this underscore here, we need the placeholders. For NumCPP, what we do is we get the number of columns, then we do a R slice to get all the rows, and then from 1 to the rest of the columns. Would be this here in NumPy. So we get all the rows and from 1 to the rest of the columns. This is the NumCPP version, and this is the xtensor version. Then, for example, to get just one value in the Y train, the Y train is just one column, so we just pass here 4. We get the index 4 here. In NumCPP, we do need to tell what column we want, because even though this is just one column, NumCPP considers this as a matrix, so we do have to pass here the 0. In xtensor, we can just pass here 4, and it will treat this as just one column. To get the shape in NumPy, we just do dot shape. For NumCPP, we also do dot shape, but it's a member function, and we can just print it right away. For xtensor, we can't just print the X shape. We need to use the index here, 0 and 1. Then to get a row the entire row, so the row 4, all the columns on that row. In NumCPP, we pass here the index of the row, and then we do a C slice, a column slice, to get all the columns. Here, it's also a view, but then we pass the row that we want, and then it's all, so xtensor all to get all the columns. Here the values are floats, and we need to use them as integer for our project. So in NumPy we convert just passing here as type in the type that we want. For NumCPP, we can just call this member function and convert them as int to get a matrix with integer values. Xtensor, we cast the matrix that we want, and then it returns the xarray as integer. To get the maximum in NumPy, we just pass here max, NumPy max, and pass the matrix that we want, the array. NumCPP, it's almost the same, but this will return ND array. To get the value, we need to ask for the item, and then it will return the single value that it's returned by max. And then we just add one here to get the number of categories. For xtensor, we need to use this a max and call it, and then we can do a +1. To normalize the values, we just divide by a constant. Here, in both cases, we also just need to divide by constant here. Simple. We need to get the transposed matrix to make easier the calculations. So here in NumPy, to transpose, we just do a .t. It returns the matrix transposed. On NumCPP, we just call for transpose on the matrix as a member function, as on the array. On xtensor, it's a function that we pass the matrix that we want to transpose, and then it returns the matrix transposed for us. Yeah, then this shape, we have seen it. Okay. To create the neural network, the shape 1 is the number of columns, and we can get here as number of columns. For the xtensor, is almost the same here, shape and 1 to get the number of columns. And this will create the random values for us. So how do we get random values? Here, NumPy, just call rand and pass the dimensions. Here in NumCPP, we pass the dimensions as one single pair of values. For xtensor, to get we also pass as a pair of values. So in this case, both are the same. Just show here the members. Basically everything just arrays. Here also X arrays. Then we need to do the one-hot encoding. So basically we create the zeros matrix, and then for the range of rows, then for the value that is in that row, we put 1 here. Almost the same here. This comment is because in previous versions, when I was doing this, this put had a problem, an issue. but then they fixed the issue and now we can just use like this. On xtensor, we still have to loop. So we create the matrix of zeros. This Amax, we call it to get the item, but then we have to loop on all the rows to put the number 1 there. And then we return the matrix transposed. Xtensor we do like this, and NumCPP we call transpose as a member function. After the one hot, we do the forward propagation. Let's see here. Basically, forward propagation is the dot product of the first weight with the input and sum with the bias, and then here is just a call for dot, almost the same here. Then let me do everything first. The ReLU we call maximum. We compare 0 with 0, so all negative numbers are gonna be replaced by 0. The ReLU here is also a maximum, so basically the same. A dot product, and then a softmax. The softmax here we get the exponential on the z, and we divide by the sum. By default, Python returns the sum for each row, but here we need to specify that the sum is each row. If we don't specify, it's gonna sum everything and return just one value, but we need to return just the sum for each row. On xtensor, let's see the forward propagation. So the dot product is a little bit different because we need to pass the matrix as parameters for the dot product. The ReLU is the same. We compare maximum with 0. We do another dot product, and the softmax we also need to specify that it's a row-based sum, and then return the division here. Next, we need to get the predictions. So we ask for the argmaximum as a row type. So for each row we get what's the index that has the maximum value, and here we need to tell that it's per row. Here is just the 0. With xtensor we can just pass as 0 here to say that it's per row. After we get the predictions, we need to count how many predictions we had correct. So to compare with NumPy, we can just compare directly the both arrays, the inputs, the predictions, and the y. We can compare directly and then sum to get because the correct one's gonna be true, the incorrect false. We sum all the truths and then we get the correct values. Here we need to convert to unsigned, then transpose, and then we can do the comparison, but then we have to convert as type and then call it, and then we can sum and return the item. This in NumCPP. For xtensor, there is this equal function that does the comparison for us. If it's equal, we do the sum and then we call it to return the value and not the matrix, the array. Next, the accuracy is just a division. This is the same for everything. Get accuracy the same, and then we do the backpropagation. The backpropagation, we compare with the one hot encoding the results of the second layer. We do a dot product and we sum. Then we have to also do the derivative, which is just compare with 0. And then other dot products and sum here. Let's see in the NumCPP how we can do it. We get the size. It's a column, so it's gonna return how many rows we have. Then to compare one hot, it comes as an integer, so we have to change to float. We do the dot product with a transpose, as we've seen before. We sum everything, and we get just the item, because this is just one value. And the derivative here, the comparison, is going to return an array of booleans, and we need to convert to float. Then a dot with a transpose we've seen before, a sum, and then just the scalar math. Here, in xtensor, we also get the size. To convert, we do a cast, and the dot product is a little bit different, right? We've seen this before. With transpose is also a little bit different. Then the derivative, also the comparison is going to return booleans. We need to cast to float. Then more transpose and the dot product and the sum and the scalars. The rest of the code we have seen before. Well, after the last backpropagation, we do just one final test, just to see how is the accuracy on the training data, and then the rest is just test data. It's the same. We get the matrix, we get the y and x, we normalize, transpose, forward propagation on the neural network for the test, and we check the results. And the same here, one final test after the last backpropagation. Then this, you say we can save the image, but you check the previous videos to see how it's done. But what's important is the get the matrix, get the y, x, normalize, transpose, forward propagation, and get the results. Same thing here on the xtensor. One last check on the training data. Then for the test data, we convert the matrix, get y, get x, normalize, transpose, forward propagation, and we have the final test. Now let's see how is the performance. Just show you guys here. I'm gonna do only 150 generation, but we are gonna get all the data, all the 60,000 images. The alpha is 0.1, and the hidden layer size is 10. Yeah, let's see how the performance here. So the Python script took 3 minutes and 40 seconds. Now let's see the C++ libraries. Just check here the CMake file. I added the xtensor. I added here the include path for where I put the NumCPP, the SIMD flags, and I added the compile options. Then the new libraries. For NumCPP, I'm using the no-boost and multi-thread. For multi-thread, we need the TBB. Then for the xtensor, I'm using SIMD, and I'm using TBB. And then the executables, I'm just adding the static libraries that I created here. And well, I already compiled them. Let's see if there's any change. No. I'm on release mode and I'm using GCC. So let's run this. Okay, I have to set the path for the OpenCV. OpenCV use it just for saving the images. Here, save image, but yeah, here save image, but you can check previous videos to understand more, but that's the only thing I use on OpenCV. And then let's run. Okay, so NumCPP took 9 minutes. Let's see the xtensor. Okay, so the xtensor took 11 minutes. Just for comparison, let's see the Eigen. Export. No. Yeah. Yeah, the Eigen took what, 28 seconds. Just so you know, the Eigen, I showed the code in previous videos, but it uses the Eigen library for the matrix calculations and the transpose and the dot multiplications. Yeah. Yeah, so for me, it looks like if I had to use on C++ one of them, I would use NumCPP because it's easier to integrate, even though xtensor, let me close this, guys. Even though xtensor is also a header-only library, at least NumCPP you can just do one include. With xtensor, we need to make sure we include other things. Also, xtensor has the XTL library that we have to install. On Ubuntu, we saw that it's simple because it's a dependence on the package, but on Linux, we have to downloads separated. So to integrate in the system, I think NumCPP is easier, but also the API, I think the NumCPP is closer to NumPy. How to change the types, the way to retrieve the data, the transform and the dot product, they look similar. But I was surprised that NumPy is faster than both NumCPP and xtensor. Luckily, the Eigen is still much faster than everything, than even NumPy. But I was surprised that NumCPP and xtensor takes almost 10 minutes each. But yeah, if I can start from scratch a project, I would use Eigen. Maybe I did something wrong with the setup. I don't know. You guys can tell me in the comments. But yeah, these are the options that I activated on these libraries. And yeah, if you like it, leave a like, and if you have any questions, I can help. Check out the repository. Yeah, thanks.